touch last year when you sent me an email about the Express interface. And since then, now we have an Express interface, and Joaquim is a JuliaOpt contributor.
So, thanks everybody for being here. Thanks Maya for the invitation. It's very good to be here. Okay, so I will talk a little bit about stochastic programming in energy systems. That is what we do mostly in PSR, this company that I work for. Okay. So our agenda for today, I will talk a little bit about PSR, then how we started with Julia, how I met it, then some projects that we did in Julia, a lot of jump, most of it with jump. Then a little bit of research that has a lot to do with mathematical programming, so jump is always on the core of it. Then I will talk about this algorithm. It's called SDDP, and I use jump to design that in PSR. There are a lot of other ones. Then I will talk about two other. They are in the wrong order, but that's okay. One is power system expansion, and the other one is power flow. Carton already presented a lot of that, so I'll just say a little bit. Okay, so PSR is a company that provides analytical solutions and consulting mostly in electrical markets. We're hosted in Rio de Janeiro in Botafogo Beach, and that's our little office. We're about 60 people, and this is a little outdated, but we have a lot of PhDs and masters working for us. I'm not in the statistics since I haven't finished my PhD, so I'm just one of the 60. Okay, so our core activities, we have many of them. So analytical tools is mostly what I'm talking about. It's mostly what I work for. But we also have like market analysis, strategic advice. We have a lot of people working with environmental analysis and other engineering studies that like use analytical tools. So this is what we've been working around the world. So we have a lot of projects in many countries that we painted in blue. We really like to get a new project on a new country so we can paint another country in the map. This is some countries we're working for, and more than 300 active licenses of softwares besides studies that we have been doing worldwide. So our main planning tools is those three I was going to talk today. The main one is SDDP, that is for optimal operation of reservoirs. That's really important on hydrothermal power systems. Power systems expansion with something we call OptGen, and OptFlow for optimal power flow. We usually use that for reactive expansion. So everything mostly for hydrothermal, because we started in Brazil and it's a big problem. Brazil is like 70% hydro, and operating that in the correct way is very hard and very different from what is a pure thermal system. Okay, so how do I start it? Like in 2015, I arrived in PSR, and when I was there, before that, I learned to program in C, but as a controls and telecommunications engineer, I had hundreds of thousands of hours working in MATLAB and R. So the day I arrived at PSR, Mario, which is my boss over there, he said, "Oh, so do you know about Julia?" And unfortunately I said, "No, I don't." So he was a really big enthusiast of the language, and he showed me everything. And then I came to love it also, and it brought me here today. So in this day, what I did was implement this called a teeny maintenance model, and with my project would be do that in Jump and compare that to Moselle, which is a algebraic programming language from FICO express. So here's it, just to get a glance. It's just a really simple model with a few constraints and integrality conditions. So we have this meet reserve, and something like you have to do commitment to do maintenance for some units, and you have to do that like once per year, something like that. Something really simple, just to compare some stuff. And so this was the Moselle model. It's kind of readable because it's a algebraic programming like most of others. And I did a Julia notebook on that same day. You can see the syntax is almost new because I had to translate that at some point of the time because somebody wanted to see that as an example, something like that. So it has like some stuff of the old syntax, like the curly braces, but the new syntax constraint. I omitted variable because it'd be too much. The second thing I did, like the next month, was implement some ideas from this paper from Juan Pablo. We wanted to work with bivariate functions, and so we had to build a grid with triangles, and then we did an integer optimization problem, which is over here. If you want to see, you can check one of those. So after that, the third project was something we call Optifolio. It's a portfolio optimization for power systems. It's based on like optimizing decisions on trees and a lot of stochastic data. I did all of that with Jump and CBC at first, because in PSR we use Express and we didn't have an Express interface. So that was one of the first motivations for Express.jl. Because problems got bigger, CBC was taking like 2 hours to solve them. The first thing I did was like write a MPS file, give it to Express. It will solve that in less than 5 minutes. And then I read like the outputs one by one. But at some point that was inefficient, and building the interface was the good idea. After that, my graduation project was a lot to do with SDDP, and I wrote a notebook for that. It was like a simple example, and it turned out to be this technical report, modeling power markets with multi-state stochastic Nash equilibria, that I presented at ICSP. Is the International Stochastic Programming Conference, where I met Miles real life for the first time. So this is the sub-problem that I wrote in Jump. It was really nice because Jump make it so easy to express a lot of stuff really fast. And this is very old. You can see the old syntax. I kept it over there just to show people that I've been working that all the time. In parallel, other people in PSR were also working in Julia. We also have people working on Monte Carlo methods for reliability analysis. We started with Python, but Python was too slow for Monte Carlo, so Julia was the best option. Then we did some stuff with optimal power flow with the help of Maria Lujan, Lucas, and Igor. I will talk about later. About research, we have a lot of other projects, many of them in Julia. So power system expansion in OptGen uses something, it's called SDDP, which is this similar algorithm but for integer programming. I'll get to the algorithm later. Reliability analysis turned out to be another graduation project. Power flow was another graduation project that we added progressive hedging very easily, Jump making everything easy. Another project that did not use Jump in full was representing like immediate cost functions. This paper over here. It was all in Fortran, but we used Julia and polyhedra to do some computations behind it. And these other two papers were in ICSP, were all modeled in Julia and Jump. It was only possible to take like 2 papers because of doing everything in Jump was so faster. Some real projects that we've been working on that really use Jump and Julia, they made it possible, was we are making some tools for Peru Energy Ministry that is SDDP and a new version of Power System Expansion with OptGen, everything written in Julia. Another project was this one for the Nature Conservancy, where we did some portfolio optimization and hydrobasin optimization for the Magdalena Basin in Colombia. So it's a book, there's a chapter over there, and we use both Optifolio and Power System Expansion, which were both written in Jump. So more industrial applications of that. And currently we have 2 more works that we have been working. One of them is evaluating Latin America interconnection, which is a project for Inter-American Development Bank. And the second one, we are refactoring some large-scale reliability model from NWPCC, which is a agency around that takes care of the Columbia River Basin. And we are working towards a new model, and everything should be on Julia. And all the commitment models will be solved and built with Jump. Okay, just a little information of power system operation modeling. So this is just a big slide with a lot of words just saying that modeling power system takes a lot of details. So you have a lot of physical parameters for hydro plants, thermal plants, and renewables and transmission network. You have a lot of details you have to consider. And doing that, adding all those details in a mathematical program in some low-level language is a pain. So doing that on higher-level languages with algebraic modeling is much better. And there's also stochasticity, and that makes everything more crazy. So using a high-level language was really, really good for writing that. The problem, one big problem with hydrothermal power system operation is that hydro plants have reservoirs, which is not a problem, it's a good thing, but that makes the whole problem coupled in time. And also you have stochastic variables like inflows. You can think of rain in rivers and reservoirs. So you never know how much rain is coming, so your problem is also stochastic. Now you have a big multi-stage stochastic program, and to solve that there is this nice algorithm called SDDP, which stands for Stochastic Dual Dynamic Programming. It was developed by Mario Pereira, PSR founder and current president. SDDP in ICSP has 5 dedicated sessions and 22 talks. Shabir Ahmed made this computation, so it's wrong. We can pin on him. In Julia, we have at least 3 public versions of SDDP. One by Oscar over there, and one by Benoit, and one by Vincent Leclerc group. I think they're maybe merging this. Let's do, I don't know what they're going to do. Oscar knows better than me. And there are many others being developed. It's like an SDDP boom. At least in my university, there is another 2 people working on that on separate projects. I don't know whether they're going public or not. But so at least that I know of, there are 6 SDDP models in Julia. Apparently, using Jump to code stochastic dual dynamic programming is really good. So, just a little bit about the problem. This is a very, very simplified version of the problem. You have an objective function that here you're coding costs and generation of thermal plants. So you multiply them, you have the costs of operating your thermal plants. you have this thing that is called the future cost function, which means if you're keeping water, this is the value of your reservoir at the end of the stage, and this is the inflows, the predicted inflows for the next stage. So if you're keeping water for the future, you kind of have some value of water, because keeping water sometimes is good, because you don't have to use your thermal plants later. There's this state space equation which encodes like, okay, your reservoir volumes in the future are equal to your current values plus what is raining over there, minus what you're using for energy production. This is just encoding load balance, so thermal generation plus hydro generation equals to demand minus renewable generation. And this is the stochastic model. There are many possibilities of model. This is just a AR2 model to represent the inflow stochastic model. There are many, many more details, so representing a very complex model is really tough. Only in this water balance equation you can have much more. You can have like irrigation, infiltration, evaporation of water, and all of that make everything harder. So it's really hard to maintain and experiment and add new features in a low-level language, as the current SDDP, which is commercialized by PSR, which is written in Fortran. It's a lot of work adding and testing new ideas, but we keep doing that anyway. But with a Julia model, that makes everything much easier, and we've been testing a lot faster, and a lot of new ideas have been coming. Just to get a glimpse of how SDDP works, given this, what we call a subproblem for one stage, this is just a problem for one stage and one fixed scenario. You decompose all your stages and all scenarios in problems like that, and how you couple them. You couple them in two kinds of iterations. One thing we call forward simulation, where in each scenario you move forward in time, solving each problem chronologically, and then you get states, which are basically volumes of hydro plants, and you propagate those states until the end. And then you do a backward recursion. In this backward recursion, we build iteratively a lower approximation for this future cost function. This is where dynamic programming comes into place. The dual part is that we do that with hyperplanes and calculated by LP duality. So we just add supporting hyperplanes for this function to represent it. And then you can do some convergence checking. It's a very interesting algorithm because it's very amenable to parallelization. You can parallelize like everything, all the stages or scenarios. You can run that asynchronously. There are many options, and we've been running that on computer networks and cloud systems for a while, because problems get really, really big, and solving them on notebooks, it's quite infeasible. Just some applications. I won't go too deep on that because we don't have much time, but you can read that later. The slides will be posted. Okay, not very good, but there should be a shadow of a future cost function over here, and over here. Maybe it's too light the color, but okay. So how the algorithm works? First, you sample some scenarios, and then you move in time, getting states that are represented on this line. This line here is cost of your function. So you propagate your states in a forward iteration, and then you go to a backward iteration. When you get cut, you keep creating cuts to approximate your function. So you propagate your cuts. This figure is showing something that it's not being seen here because of everything is too light. This cut in the last state is usually tight to the to the lower bound of the approximation of the so-called future cost function. But the other states, it doesn't get tight for the first time because you're solving an approximation of the problem. So you keep adding cuts, and then you go forward once again, and then you go backward once again, and you go building your future cost function. Here we're showing a better cut was obtained by the better approximation here. So this is just to get a glimpse of the algorithm, so I can talk about some stuff later on. This is a figure that I like to see because I like how do I see parallelizing that. One possibility is you can parallelize everything on stages. So when you are in the second stage, you can solve all these problems for different scenarios in parallel. In the third stage, you solve all the problems and scenarios in parallel. You can do that. Or you can do like, for each scenario, you can go asynchronously and solve all the problems. So many options and very amenable to parallelization. So why Julia and Jump? Okay, once again, easy to prototype and test new features. It has very good performance. Python would be easy to prototype, but not so much good performance. And I'd like to quote Miles a few times in this presentation. One of them is like, I want to do to model and solve LP within programming language, but Python is too slow and C++ is too low level. In our case, we think Fortran is too low level, but we also have a version of the model in C++. Miles again. I want to implement optimization algorithms in a fast, high-level language designed for numerical computing. So we have been doing that. Thanks, Miles. This is just an example of a big, not a big problem, an average size problem solving Central America. Each of the subproblems for each stage and each scenario has 2,500 variables, and there's an extra zero here, my bad. So it's 25,000 constraints, not 2,500,000. 60 stage, 100 scenarios, and 5 iterations. That means a subproblem is built in Jump more than 200 times, and a subproblem is solved by a solver more than 1,000,000 times. So it's very critical to have good performance everywhere. Sending solver information, getting information from the solver, building problems. Okay, nowadays we got very good results. We are keep improving them every day. Currently, more than 70% of the time is inside the solver. So Julia is doing a great job being really fast everywhere else. I could see that thing to timer outputs package. It's a very nice package if somebody doesn't know it. And something really nice is that after making everything, making run in parallel was really, really easy using MPI.jl. I think there's a lot of people here that work on that. I know that Joey has worked a lot of that on that struct Jump. So thank you for start moving with that part. It was really easy to do that. A little bit more about implementation. Something else that Miles said that was really nice is make it easy to access low-level features. Don't get on the user way. Because sometimes Jump is very, very flexible, but sometimes you want to do more with models. You have like more parameters you have to deal with, a lot of stuff you want to do. So it was really good that we could get into matprog base and add extra stuff. And some stuff is like, for SDDP, you get a lot of Bender's cuts for the approximation of the future cost function. So you have this thing called a cut relaxation or a cut selection algorithm that you only add to your problem that the cuts that are the most tight ones, and you keep adding them iteratively instead of adding all of them at once. So doing that with Jump was a little bit slow. So you can go just through matprog base level, and that's a thinner interface, and you can add a lot of cuts much faster. At first, I was naively building all the problems, but you can change that and not build that many problems, because in average SDDP model you can build you build a jump model, which I mean everything from writing the add constraint, add variable functions to getting everything into the solver would take like 4.5 milliseconds, and solving the problems would take 0.4 milliseconds, because sometimes the problem is so easy and dual restart is really fast when you're just adding cuts iteratively. So it's too expensive to write problem for each scenario, so you can build problems once and just change the model with a lot of flexibility that Jump has. You can change right-hand sides, add constraints, but once in a while you get to some problems that you have to do more stuff. And instead of building I was building the problem once a stage, I had to make copies of the model because Jump could not delete variables. Making copies of the model was faster than building the problems from the beginning. But then I came up with the idea of removing constraints that a lot of people do already. Jump doesn't have that feature, but that made us add that thing to matprog base. So now matprog base works with deleting constraints, deleting variables, and changing coefficients. Jump works with fixing values. So those things were motivated, at least for me, from this kind of problem. Other stuff that Jump allows you to access is you can change parameters and tolerances. And more stuff I had to do under the hood behind Jump was fixing globals. You solve an integer problem, but you want to get duals for that, so you fix integer variables, and then you go back and solve the problem with that fixed and get the dual variables for that. In-place getters. Most of the APIs in Julia, they create, every time they get a solution for you, they create a big value, a big vector to keep your solution and return the solution to you. But if you're solving too many problems, that gets on your way, and doing that in place sometimes is faster. It was like 5% was not a big bottleneck, but you can get rid of 5% of the time. Why not? I'll go really fast to the last two models because I don't have much time. So one of them is power system expansion planning. The original model was in Fortran, and these two problems were written in Moselle, so it has this integration between the two. But this is just a scheme of how the old model would work. This is some applications. But the new model is a completely rewrite. We did everything from the beginning, everything in Jump and Julia. We added new features because the model had to work and find good values for something we call reserves of power systems. We have already used this model in Rio studies in Saudi Arabia, Colombia, and Chile. The new model has yearly sub-problems instead of a big problem, a big decomposition problem, which the old one works. And Jump is heavily used to model a lot of details that come into the problem. This problem also motivated us to work into other stuff, is callbacks in Express that I didn't do for the first time, so I'm starting to work on that right now. It's a lot of work to do, and integrating that with Jump is hard because Express has a different interface than Gurobi and Cplex, so maybe here we can talk about that and improve and get everything better. Something else is IIS, because these problems are really big and sometimes it's important to find IIS for them. So maybe writing an interface for that. I made a little interface for Express that I'm planning to go public soon, but it's not ready now. The problem has already been converted to a decomposition technique called the SDDP. It's a paper from Xavier Med. It's a very interesting paper. It's an integer version of this SDDP algorithm. It was really easy to add that to the model if you have everything coded in Julia and Jump. This is the last model, so I won't go too deep into that. It's just the original version is a tailor-made interior point method algorithm. Everything written in Fortran with all the Hessians and Jacobians, everything got by hand. So adding new stuff to this model is really hard, and testing new formulations like Carlton was showing us is extremely hard, although this is super fast, the original model. But doing that on the new version of Julia, you can not only use those the convex approximation models to generate valid cuts for decomposition algorithms, which is something we like, but also you can implement new strategies like progressive hedging, as I talked earlier in the talk. So the idea is something like power models. We started doing that before we knew about power models. So we abstract on types of constraints, and so we have SDP models, SOCP models, and we could write a lot of that in Julia super fast also. This is just some results. It's like the Fortran algorithm is way faster. In this example, we solved like 12,000 problems sequentially. The Fortran did everything in 160 seconds, but it's tailor-made, so it should be much faster. And this is times for what we did in Julia. Still, the solver takes much more time, so it's not Jump's fault, at least. It's just that the tailor-made algorithm is much faster than generic algorithms for these problems. But we think we can get better results than this, just with some tweaking and some stuff that Jump already exposes to us. And we're working towards that. So that will be the end. And thanks more, everybody.
You have time for like 1 or 2 questions?
So I was curious, you mentioned the SDP relaxation, and I didn't see any results for it, but in power models, I tried implementing it, and just the vanilla kind of one was just really, really bad.
Yeah.
So
the solvers are not that good for SDP compared to what they are for nonlinear. We have seen the same thing you've seen. Like IPOP finds the best solution super fast, almost always. So SDP is super slow. SOCP, you can get better times, but SDP is really, really slow.
I was just wondering about supporting Julia in production when you're giving it to clients.
Currently,
How does that work?
we are not giving them into clients to work in computers because most of the problems are really so big that you cannot solve in your computer. The problem I showed that I solved in 20 minutes in my computer was actually a very simplified version of Central America. It didn't even consider linear power flow, that it's very usual in these problems. So we usually solve them on Amazon. So what clients do is that they give the data to a web interface. This data, when they press run, this data goes to Amazon, where there's a server ready with the model installed inside of it. It runs on many computers, gets back data to some database like Amazon Redshift, and the clients can view the data with Tableau or something like that, or download if they want. But sometimes there are terabytes of data, so it doesn't make sense to download, just visualize and see whatever it is.
So they don't see the code for the SDDP?
Not currently. We don't know what we're going to move in which direction.
Okay, let's thank Joaquim.